If we've covered binomial distribution in statistics, then binomial hypothesis testing is the next step. We'll be using those concepts that we covered to deal with data from scenarios where there's only a binary outcome, to then check if something about that scenario is indeed true. Usually the probability is the probability as stated, or might it in fact be something else. Now, if you haven't covered the regular binomial distribution in statistics yet, I would highly advise that you do that, because we are going to be working with a lot of the concepts covered in that initial introduction to the topic. All the same, I will explain things as we go along, yet you'll have a better understanding, a better basis, if you're coming at this with that understanding already in place. Either way though, what we'll do today is just start off by looking at some definitions actually. So, some questions may in fact ask you to give definitions of these terms, so what does this mean, in which case you will want to have a firm enough understanding in order to give a definition. But even if you don't come across those, it's still good to have this understanding, just for your own sake of clarity. A test statistic is a statistic calculated from sample data in order to test a hypothesis about a population. So when this statistician has gone out and gathered their research, has talked to different people or investigated different things depending on the subject of that investigation, they'll have the individual pieces of data. But in order to then really give conclusions about this, they need to come up with some statistic, some probability or value. That's what we're referring to with these test statistics. So again, in this case, in these questions, it's probably going to be what was the probability of X, Y, Z happening. Meanwhile, a hypothesis test, which again is the whole name of this part of the topic, so it's probably best we know what it means, is a test used to determine if there is evidence that sample data is representative of a population. So when the statistician has gone out and done their research, unless they're doing a census, they will not have looked at every single person or every single thing within that population. They will have selected a sample group, which in theory should be representative, and then taken the data from that and come up with a conclusion. And then because hopefully the group was representative, that conclusion should reflect the actual trends in the entire population. But we need to check this, and this is what we're doing with the hypothesis test. So yes, it's determining, is there evidence? Again, you may not be 100% certain of this, we're just looking for, does this seem to be the case, or by contrast, is there not enough evidence to support it? There not being enough evidence doesn't necessarily say it's not true, but just that we can't make that claim right away. Now, when you're doing your hypothesis test, you may come across something called a critical value, and we'll define the critical value as the point on the test distribution that is compared to the test statistic. Basically, when you've taken your hypothesis test, from the sample group that you are working with, you will come up with your own value in your own calculations. This is what needs to be compared to our test statistic here, and if it falls on the right side of an inequality sign, which we'll come to later when we come through the questions, we'll be able to say that yes, okay, this does seem to suggest that our hypothesis was true, or by contrast, that there isn't enough evidence, so we're not going to say it's true for now. But then there's actually a second kind of hypothesis test we can do with this first one, being say find a critical value and compare. But alternatively, you can find a critical region. Now the critical region is the range of values corresponding to the rejection of the null hypothesis. There are, in these questions, two types of hypothesis, and every hypothesis test must have both. The null hypothesis is what is currently believed to be true, so what do we currently think the probability is, for instance. The alternative hypothesis is then what new suggestion you have, what might be the case instead. This is the thing that you are testing for, to check. In order for the test to succeed, as it were, for the alternative hypothesis to be accepted, the null hypothesis, what is currently believed to be true, must be rejected. Now the critical region is not a specific value, otherwise it would be the critical value. The critical region is instead just saying if the value that we got when we did our research fell within any of this range, then that would lead to the alternative hypothesis being selected. So critical value is a specific number. Critical region is an inequality expressing a range of values which would tell us which conclusion we would make. Again, obviously we're going to get examples of these as we now go through the following questions. First up, what we have below us here should be familiar from the general model of a binomial distribution. So we have a variable x being distributed binomially, and then we have two numbers inside of brackets, the first one being the number of trials and the second one being the probability of success. So in this scenario, something is tried 34 times in total, and the probability of success is 0.59. Now in actuality, there were 26 successes, as it were. Now, test at a 5% significance if the probability has increased. Now, when we talk about significance or significance level, you don't have to worry so much about where this number comes from, whatever the percentage is going to be. Just understand that, in essence, this is the question telling you, we have determined that this is the probability that you will come to the wrong conclusion, that there wouldn't be enough evidence to support whatever claim you're testing for. It's something that you'll only need to focus on later on in the question. Again, when we do that, it should become a lot clearer what is meant by it. But for now, just to get out the way in acknowledgements of, it is in the question. I'm not going to leave it entirely as an unknown until we reach it in the method. To start off with, though, we need to create our two hypotheses that I mentioned above, the null hypothesis and the alternate hypothesis. That should always be your first step in any hypothesis testing question. So for your null hypothesis, which we're going to represent with a H and then a small 0 in the corner, in this case, the null hypothesis, that which is currently thought to be true, is that the probability is 0.59. And in general, the probability is going to be what your hypotheses are based around. However, just to reaffirm, we are testing if the probability has increased. So it's the probability that is potentially wrong. With that in mind, our alternate hypothesis, which will now be a capital H with a 1 in the corner, that's going to be the probability, and since it's increased, we'll now say that it's greater than that 0.59. The number is always going to match, but it will be a greater than symbol if it's increased, less than symbol if it's decreased. There are circumstances where it will just say that it's changed. It won't give an indication of greater than or less than, and we'll get to those in a subsequent example. In this case, though, since there is an inequality, and because we are working with the binomial distribution, that should remind you from last time that we'll therefore be working with binomial CD. So you'll need to get to that section in your calculator once again. For this, we're going to need an x, n, and p values. X we know equals 26, n we know equals 34, and p we are going to take as what is currently thought to be the case, so that's 0.59. Next, we'll actually set up the notation for a probability that we're looking for. So it's going to be the probability that x. And now the inequality sign inside of this probability matches the direction of the alternate hypothesis. That being said, whereas the alternate hypothesis is a strict inequality, so it's just greater than, in this case, in the hypothesis test itself, it's always or equal to. Okay, so same direction as the alternate hypothesis, but with an or equal to in there. Then again, this x that we're testing against is our 26. Now, if we recall again from last time, in your calculator, when you do the binomial CD, your calculator will only work with less than or equal to. So we're already going to have to rewrite this slightly. We'll have to say that that's the same as 1 minus the probability that x is less than or equal to 25. So in your calculator, if you do your n is 34, p is 0.59, and now do x as 25, you'll end up with this being 1 minus 0.9898, which will come to 0.0102. Once you have this, this is your critical value, that which we were talking about in our definitions up here. It is this critical value that we're now going to compare to the significance level. This is where that part of the question is now coming in. So as a decimal, if you want to make it easier to compare that way, 5% would be 0.05. If we were saying before that if your probability was greater than this, then it would seem that you are potentially incorrect in your conclusion. That would mean we have to stick with the null hypothesis. We're looking to compare these two basically. In this case, our critical value is less than the significance. Therefore, we will take the alternate hypothesis. There is evidence that the probability has increased. In general, if your critical value, like in this example, is less than the significance level, therefore, we will say that there is enough evidence to take H1 to reject H0. However, if your critical value is greater than the significance level, then you will keep your null hypothesis. There is not enough evidence to take the alternate. If we were then just to try to apply these principles on another question then, we could have something that's a bit wordier rather than just giving you the strict mathematical notation there. So the probability that a chocolate in a box contains nuts is thought to be 0.6. Out of 50, 35 turn out to have nuts. The probability is thought to have changed. Test to check at a 10% significance level. So, once again, because it's a hypothesis test question, we need to start just by labeling out our hypotheses themselves. So for our null hypothesis, we're looking for the probability because we're checking that's what's thought to have changed. Probability is thought to be 0.6. But here, for the alternate hypothesis, because it's simply thought to have changed, there isn't an indication of increased or decreased, we'll simply say that it's not equal to 0.6. Now, when it's not equal to, we're going to refer to this as a two-tailed test, therefore. What we had in the previous example was a one-tailed test because we were simply looking either at it being less than or greater than. If we were to draw out this probability distribution, we'd only be looking at one side of it, one tail. But here, because we don't know which direction it may actually be going in, we have to check both directions. We have to check both tails. Now when we do this, the 10% significance level we're going to be looking against at the end, that represents both tails together. So if you have a just not equal to find the value that you're going to be comparing your critical value against, you need to halve the significance level. The significance level we're going to have is only going to be 5%. 5 for each tail. Now next is when we would identify our x, n and p values. So x is going to be that 35, whereas the n is the whole 50, and again the p is going to remain what we identified before, so this 0.6. However here now, whereas before we could simply set up a probability notation of x is greater than or equal to 26, because we don't have a direction here, this time when we set up our probabilities, we need to do one of each. Essentially we're going to do the method twice. So once we're going to do it where x is less than or equal to 35, and then we'll do it again where x is greater than or equal to the 35. Now, in each case, I'd like it if you could now just pause the video and have a go at them for yourself. So work out what these probabilities are actually going to be using your calculators and the numbers above, and then compare them in each case to the significance level. And based on these, because it's a two-tailed test, we only need one of them to, one of the critical values to be less than the significance level in order to take H1, to take the alternate hypothesis. So you're just looking to see, do either of them end up less than the significance level? If they do, then think what conclusion. If they don't, think what conclusion. So just have a go for yourself, then press play again when you're ready to compare. So in the first instance, where we had our x being less than or equal to 35, that's just a simple matter of putting 35, 50 and 0.6 into the binomial CD section of your calculator, and that should get you 0.9460. This is very much greater than the 0.05, therefore we won't be taking that as any kind of evidence of the alternate hypothesis. As for the other side, because this is a greater than or equal to, we're going to need to switch it around. We'll need to make it 1 minus the probability of x being less than or equal to 34. This, if you put it in your calculator, should get you 1 minus 0.9045, which would then equal 0.0955. This, again, is greater than the 0.05. It's much closer, but it's still bigger than it. Since both of these are bigger than the significance level, both of them are telling us to keep the null hypothesis, that there isn't enough evidence available at the moment to change our minds. Okay, if we were right with that, well, we can see how these are both critical value questions, how we have used our binomial CD to get a specific number based on an x value from the scenario, and compared that to a significance level. If we're good with that, let's now move on to examples of the other version which I mentioned before, which would be the critical region. Now, if we just read through these questions first, again, just get a sense of them before we get into the actual method. There are 64 dogs at a park. It is thought that 53% of these dogs are female. One owner believes the true probability is actually less than this, though. For a significance level of 5%, what would be the critical region? And once you have that, what is the actual significance level? Well, because this is still a hypothesis question, based on the fact that we have a significance level and critical region this time, we need to start by identifying our hypotheses. So for our null hypothesis, because it's the probability, once again we're looking at changing, we'll say that P equals, and we'll just turn this 53% into a decimal, just because that's what we're more used to using and what you're going to plug into your calculator. And then for your alternate hypothesis, because the owner believes the probability is less than this, we'll have P is less than 0.53. Then we know for certain that N is going to be 64, because that's how many dogs there are in total. Our P we're going to take as that 0.53, and the significance level we'll have as 0.05. Since this is a one-tailed test again, since it's just a strict less than rather than a general not equal to, we don't have to change the significance level in any way. Now, we don't have an X value. We don't know how many dogs were actually female, not yet anyway. And that's why we're looking for the critical region instead. The way to go about this, you can basically just think of it as trial and error, really. If you go back into your binomial CD section of your calculator and plug in this N and this P, what you're going to do is just try out different X values and find what's the biggest X value that still has the probability at the end being less than this 0.05. If you do this, you should find that the probability of X being less than or equal to 27 is 0.0540. Now, this is very close, however it is still greater than the significance level, so we're going to have to drop our X value another value to get to P being less than or equal to 26, since this would give you 0.0316. This is less than 0.05, and since this is talking about number of dogs, so it's a binomial distribution in general, you can't have a decimal value in here, so 26 is the biggest number that leads to the probability still being less than 0.05. Now, to be clear, there may be some rare question that it specifies it wants you to find the X value that is closest to the significance level. If this had specified closest, then you would have gone with a 27, kind of overriding our usual rules about having to be less than, but it's only if it specifies that you would go with this instead. In this case, we're saying that X has to be less than or equal to 26, but we also know that x can't be less than 0 because there can't be less than 0 dogs. So strictly speaking, this here would be your critical region. If x was indeed to fall anywhere between 0 and 26, then that would be enough evidence of the owner's claim, and we would say therefore that there are indeed there is a lower probability of having a female dog in the park than the currently assumed 53%. Now that we have this, we can go on to state what the actual significance level is, because there isn't an x value that would give us a precise probability of 0.05. Instead, we want to know what is the probability we can get out of the x. Well, that's actually the 0.0316. We already have it as part of our working. We just now need to point it out as being the true significance level of this scenario. If this had been a two-tailed test, then you would have had to add together the two probabilities that you had found for either of your critical regions, because in a two-tailed test you'll have a critical region down the bottom end of the probability and up the top end. But yes, just once you've done your working, just identify what was the probability you actually got out that fits your criteria and state that as the significance level. With this done, the question may then give you an actual x value to work with. So now we're told that in fact only 8 dogs were female. Comment on the owner's belief. Well, 8 falls within this critical region, and this critical region was saying the x values that would validate the alternate hypothesis. Well, since 8 is in here therefore, that means there is enough evidence to the alternate hypothesis. The owner's claim should be true, that there are indeed fewer female dogs in the park than a claim of 53% should lead us to believe. Okay. Now if we just go with that, we'll just have one final example. Again, I'd just like to see how you can get along with this on your own, thinking about what we just did with the critical region, as well as thinking what we had to do with a two-tailed test last time. So a cafe believes that 9% of their customers buy lemon tart. The manager believes it to actually be different. They take a sample of 79 customers, find the critical region of a two-tailed test at 6%, at a 6% significance level, and what is the true significance. Once you have that from the sample, 3 buy the lemon tart. Comment on the manager's belief. So just pause the video, have a go for yourself, and then press play again when you're ready to compare. Right, so for one last time, to start off with, we need to identify our hypotheses. For our null hypothesis, we're going to have the probability equals 0.09, the 9% as a decimal. Meanwhile, the alternate hypothesis is simply going to be that p does not equal 0.09, both because the question has in general specified that this has to be a two-tailed test, but also because there's been no indication of whether this probability has increased or decreased. With this, we can then specify our n, p, and significance level. So for n, that's going to be your 79, your p, that 0.09 from before, and then the significance level, because it's a two-tailed test, once again we're going to have to halve this percentage here, so it's going to be 3% or 0.03 in either tail. Another consequence of it being a two-tailed test is that we'll need to consider both the less than and greater than options. When doing the less than, so the probability that x is less than, and we're trying to find a number that will make the probability less than 0.03, if we were to use 3 as a starting point, that would get you a probability of 0.0671. This is greater than the significance level, so we're going to have to drop our value a bit. Let's now try x is less than or equal to 2. This would get you the probability of 0.026. This is less than the significance level, and because x has to be an integer, this is the highest number that will work to be less than the significance level. Therefore, the critical region for the lower tail of our distribution is going to be x's between 0 and 2. Now, as for the upper critical region, because we're going to be looking at x is greater than or equal to, this essentially we're going to be using our 1 minus the less thans. So if we had 1 minus probability of x being less than or equal to 11, you get 0.0498. Well, this is greater than the significance level, so we're going to have to move on. To do 1 minus the probability that x is less than or equal to 12 next, therefore, that gets you 0.0238. This is less than the significance level, so this is what we're going to take. However, we just must clarify that because we're after the greater than or equal to specifically, this is the same as the probability of x is greater than or equal to 13. Now, since x is greater than or equal to 13, that makes 13 the lower bound of this upper critical region. So we'll have that 13 is less than or equal to x, which in turn must be less than or equal to 79, because that's the maximum number of customers that we can have in this scenario. These then are both of your critical regions. If x is any of 0, 1 or 2, and then anything between 13 and 79 inclusive, that means that there is enough evidence that this 9% claim is wrong, that the manager is right. However, if x was anything from 3 to 12 inclusive, there would not be enough evidence, and we would stick with the 9%. Just to get what the true significance is next though, this is where we just add up these two probabilities here. So our significance level is going to be 0.0226 add 0.0238, which will be the same as 0.0464, or if you prefer as a percentage, because that's what the significance level has been given out before, 4.64%. Finally, from the sample, 3 actually buy the lemon tart. Comment on the manager's belief. Well, 3 was in that interval that I just mentioned before. It's in neither of the critical regions. Therefore, there is not enough evidence to support the manager's claim. Therefore, it's likely that the manager is wrong and will stick with the 9% that we had before.